Welcome, and we are very excited today to talk to you about vendoring PyData for enterprise software supply chain. My name is Zayd Ma. I'm presenting today with Hussain Sultan. Currently, I'm a technical program manager in the United States Air Force, specifically with the 309 Software Engineering Group. I came from a background in academics and physics, which lent itself to a lot of data analytics, and that has fed into the problems that we're facing today in the Air Force we have petabyte scale data problems of where we're not analyzing our data to its maximum efficiency and potential. So over to you, Hussain.
Thank you so much. I am Hussain Sultan. As Zayd mentioned, I'm a PyData consultant collaborating with the Air Force and Zayd's team in transforming and modernizing the data analytics infrastructure as well as the analytics processes. I previously come from the world of the banking, where I institutionalized the PyData tools in the enterprise setting in regular and compliant environments. I am very excited to be here today to talk to you guys about some of the innovation that we are doing on the vendoring PyData tools for highly secure environments. Back to you, Zayd.
All right, thanks, Hussain. So the problem that we're facing is we have, like I said, we have petabytes of data in secure environments, primarily high-dimensional time series telemetry from avionics. That's not the only data type we have, but it is our primary focus right now. And there's a lot of really good and powerful tools in the open source world, and we'd like to bring those tools and techniques to our domain challenges. However, sitting in the middle of that is the software supply chain. So how do we take all these amazing tools and move them into our secure environments? And so what comes along with that in the Air Force, there's a lot of regulations that we have to deal with. Cybersecurity is obviously a big concern. How you package up and deliver that software is important. How those environments are actually connected can create problems. And we need to do all of this with minimal operational overhead so that it doesn't become an undue burden to actually make this a reality. But okay, given that we can move it, then once the open source tools are on now next to our domain challenges, we will quickly identify any gaps or problems that those tools have for our problem sets, and we would feed those back to the community either through direct contribution or through engagement. So the bottom line is that we want to have a process to rapidly instantiate robust data science tool sets and data platforms in our secure environments to meet some of our very real challenges that we have today. So in that software supply chain problem, there's steps to this. So you have to package and deliver the software. Then you have to scan it and make sure that it doesn't have malware, ransomware, or contain threats that could happen downstream after maybe we'd make software and deliver it to someone else, and now that adds new problems. So all those things are concerns. And then on top of all that, you then have to document everything you've done through software bill of materials and dependency checks and audits and documentation and so on and so forth. And so in the current conda ecosystem, there's not a good way to do that, and so we have built a tool called conda-vendor to help with the SCA and documentation piece of it. And I'll hand it over to Hussain to demo.
Awesome, thank you so much. As Zayd mentioned, that we created a new tool out in the open source. It is available in the Conda Forge. The tool is called the conda-vendor, and the premise of it is that I as a data scientist may have a conda environment, a YAML file, and I want to be able to use that environment to just solve for it at a place where I may not have internet access or in an air-gapped environment. In order to just solve for that problem, our approach is that we just start from an environment YAML file. In this case, I'm just showing you a simple environment with pandas in there, and then we go to a two-step process. The first step essentially takes that environment, the YAML file, as an input and outputs a meta manifest. The second step takes that meta manifest and outputs a local channel that can be used for offline work. So what it basically means is that once you have the local channel created, you can pass the -c flag to kind of create and be able to create your channels from, your environments from an offline, completely air-gapped environment. Some of the features, as I mentioned, we do create offline channels, but we also mirror the upstream patch repo data, the JSON, so that we can have the correct dependencies and help the solver with that. It is designed with a GitOps pattern in mind, and hence why we have a YAML file in the middle that drives the second step of mirroring the channels. We also support multiple architectures, including Windows, and these local channels can then easily be like mirrored to Artifactory or Anaconda Teams products as well. So how do we do this? The first step I briefly introduced earlier. What it amounts to is that it will take the environment, the YAML file, and create a kind of log file under the hood. Using the log file, we have the minimal spec that we need to recreate that environment downstream. And we output a lot of that information along with some other metadata, as example, the license types, MD5 or SHA-256 information about those packages in this meta manifest.yaml. Once we have that meta manifest.yaml, we can now create, we can now use that to actually create the local channels. And in that process, we also download all of the tarballs and validate the SHA-256 checksums that were derived from manifest.yaml. Here's more detailed process flow. I'm not going to go into it in this talk, but in lieu of it, I will show you a live demo. All right, so I am in a fresh environment. I will go ahead and install conda-vendor. And at this point, it's just, you're going to download it as a conda package from conda4 channel. Conda-vendor is already available there. Awesome. So now we already have this package. Let's look at a example environment.yaml file. And in this case, we're just adding pandas. But let's, for the sake of it, also add matplotlib. Okay. Once we have the environment created, then we can do conda-vendor and call the meta manifest. And we can then pass the environment file with -f file, -f flag. All right. So now you will notice that it automatically defaulted to the OS x64 platform. It has the specs correctly identified, and it also identified the channel that it is going to mirror. So at this point, you're going to run the conda log under the hood and create the minimal specs and then output them in the meta manifest file. So let's look at the meta manifest file really quickly. This is the same structure that I showed earlier in the PowerPoint slide, but we can essentially just like go through it and do an eyeball test. So here we have all the information about our packages, including the dependencies, MD5, SHA-256, as well as the license type and license family information. Awesome. So we have that. Now, once we have created this meta manifest file, now we can essentially use that as the input to the conda-vendor channels file, the channels command. Channels, and we will pass the meta manifest file with a -m flag. And what this will do is that it will create a mirror of this channel that I can then use locally. And it will, in my case, it is just going to download it here. So this is my complete path to this channel that I will be able to use downstream to actually create this environment again. As the the process is done, so now we can go ahead and look at and examine the structure for our local channel. And here's how that will look like. So we have our NoArch and OS664 channels with all updated repo data.jsons. What we can do from here is we can use this channel. So let's do conda create. We'll call a new env. So let's do matplotlib, pandas, matplotlib, and let's go ahead and call this new environment. Test. And let's not create it, and I'll just do a dry run just for the sake of the demo, so we don't actually end up creating this environment. Oh, you don't do dry run on this. Sorry, you cannot do dry run. Yes. And what this is now should do is show us a plan with all of our local files instead of using the online files. So here you go. There's all of our local main files here, and everything is coming from our offline channel. All right. So as you saw, we can have create the local channels, and using that meta manifest file. We also have an added benefit that we can use and directly integrate with a current tool called Jake by Sonatype. Jake allows us to check for vulnerabilities or and also create a software bill of materials report based on your Python environments. But now we are able to extend that to conda packages here as well by just using our meta manifest file with some ugly hack with the YQ tool, but it results in a vulnerabilities report that we can then have a discussion around or remediate the findings later. I will let Zayd talk next about the real world use case where we use conda-vendor for onboarding a Jupyter Hub to a secure environment.
Thanks, Hussain. Yeah, so before I talk about specifically how we've been using conda-vendor in this pipeline, I need to back up and talk about what Iron Bank is, for those of you that aren't familiar. So Iron Bank is a trusted DoD repository of digitally signed images for both free and open source and COTS software. And so in order for a software product to be listed on the Iron Bank, there's a series of scanning and approvals that it has to go through to get there. And one of those steps, they need a hardening, what's called a hardening manifest. So anything that you put in the container, they need to know, and then they will run their own checks on that. And what conda-vendor has done for us is, as we update our data science environments that we're trying to ship into the secure environments, it automatically generates the manifest file for us with the exact set of dependencies that we actually need to ensure that that's going to function offline. And then because it's automatically generated, the Iron Bank container hardening team can more quickly process that and hopefully get our new software that we need, or not new, but the package software we needed moved and approved more quickly. And that's working today. So we're doing that today as we speak, which has been a great benefit to us. So that's it.
And you're more than welcome to check this out on the link below.
Oh, yes, please do.
Okay.
Yep, so we don't do this alone. This is a collaborative effort. Currently, it's the United States Air Force. We had the 309 software engineering group, the Edge teams working with MetroStar and QuantSight. We're also working with Coiled and TiDelift through AFWorks, through some SBIR grants. Hopefully those technologies will be providing value to us in the not too distant future as well. On the right side of the screen, I want to highlight some of our contributions we've made to open source. We've, in addition to conda-vendor, which you saw today, we are working on a project called BitNest, which will do performant binary packet parsing using Python, specifically Numba. We are also looking to use Intake to have a persistent metadata catalog for rapid querying. And as we get that catalog to a state that's more stable and we're happy with, we'll hopefully be open sourcing that as well. I really want to also highlight the public data sets we've made available. We've taken some NASA flights and they're in Chapter 10 data format, which is on a public bucket. In that bucket, there's both raw and parsed versions for you to take a look at if you're interested. So please do. And with that, please reach out to us if you're interested in talking more. And thank you very much.
Thank you, everybody.